In 1919, a loaded London double-decker rolled on a gentle curve and killed its passengers. The center of gravity sat above 1.5 meters, catastrophically high for a vehicle over 4 meters tall. Today, a modern double-decker resists tipping past 32 degrees. The engineering trick that closed that gap is one nobody explains because it is not a single clever part. It is a century of calculated decisions, and it began with tragedy. Mara Patel stands in front of a brittle, yellowed newspaper from the spring of 1919. The headline spells out a disaster. A double-decker bus, heavy with passengers, toppled on a mild curve in central London. The photograph beneath it is stark: splintered timbers, shattered glass, and a crowd of onlookers pressed against the cordon. 2 names are listed among the dead, both commuters who never reached work that morning. In the weeks that followed, city records tallied the bus's center of gravity at over 1.5 meters, dangerously high for a vehicle standing more than 4 meters tall. The bus, designed for capacity, placed most of its weight above the lower deck, turning every sharp corner into a potential catastrophe. 7 years later, the same pattern repeated itself in Philadelphia. 3 double-deckers overturned in a single month on Broad Street's infamous curve, injuring more than a dozen riders. Accident reports from the period describe upper decks packed with standing passengers, steel chassis flexing under load, and wheels lifting from the cobblestones long before the driver could react. Engineers estimated the center of gravity for these early models at nearly 1.7 meters, far above the safe threshold for such a narrow track width. For every 10,000 kilometers traveled, open-top double-deckers suffered 12 rollovers, compared to just 3 for the newer, enclosed designs. The pattern was clear. Height alone wasn't the culprit. It was the vertical stacking of mass, engines mounted high, fuel tanks above the lower deck, and little thought given to how weight distribution affected stability. Photographs from the era show buses lying on their sides, windows smashed, their upper decks twisted against the curb. Each headline, each accident, added urgency to the search for a scientific answer. Stability could no longer be left to chance or tradition. The question was no longer if a double-decker would tip, but when and how engineers could measure, predict, and ultimately prevent the next disaster. In 1933, a group of engineers gathered at London's Aldenham Works with a new tool, a tilting platform rigged to measure the precise angle at which a double-decker bus would begin to topple. Mara Patel, holding a battered field notebook from the period, explains how the test worked. A fully loaded bus, passengers simulated by sandbags, was driven onto the platform. The rig tilted slowly, and instruments tracked the center of gravity as the bus leaned further from vertical. The critical measurement: at what tilt angle would the wheels on the high side lift clear of the platform? The data was stark. With a full passenger load, the center of gravity sat at 1.73 meters above the road. The bus held until the platform reached 30.6 degrees before tipping. Unloaded, with the center of gravity lower, the same bus held to 35.3 degrees. These numbers were not just academic. Accident reports from the previous decade had shown 12 rollovers per 10,000 kilometers for open-top double-deckers, compared to 3 for the newer enclosed models. The tilt test put a number to the problem, and crucially, to the solution. Engineers set a new benchmark. Any double-decker must withstand a tilt of at least 28 degrees when fully loaded. This figure became the minimum requirement in the 1939 bus construction regulations and was later adopted into UK vehicle standards. The impact was immediate. Buses that failed the test were redesigned, engines and fuel tanks moved lower. Heavy components clustered beneath the floor. Standing passengers restricted to the lower deck. Within a decade, the rate of rollovers dropped sharply, and the tilt test became a rite of passage for every new chassis. For the first time, stability was not a matter of tradition or guesswork, but of measured, repeatable engineering. Blueprints for the Routemaster, spread out across Mara Patel's desk, reveal a deliberate break from tradition. In 1956, London's engineers committed to a full aluminium body, eliminating the heavy steel chassis that had weighed down earlier models. This semi-monocoque construction shaved hundreds of kilograms from the upper structure, with records showing a 500-kilogram reduction in upper body mass compared to the RT type. The Routemaster's panels, riveted directly to the frame, created a rigid yet lightweight shell, an innovation that let engineers concentrate mass as close to the road as possible. The rear axle was widened by 90 millimeters, expanding the track width and enlarging the stability triangle without raising the center of gravity. This simple adjustment increased the lateral distance between wheels, directly improving resistance to tip-over forces during sharp turns or in strong crosswinds. The Routemaster's design team understood that every millimeter mattered. A wider base meant a higher threshold before the center of gravity could project beyond the tipping polygon. Stability weight was not just minimized, but positioned with intent. The engine, transmission, and a 200-kilogram steel ballast plate all sat beneath the passenger floor, accounting for roughly 40% of the vehicle's total mass. This kept the center of gravity around 1.4 meters above the road, lower than the waistline of a standing adult. The result was a bus that could withstand a static tilt of 29.2 degrees in official tests, exceeding the regulatory minimum of 28 degrees set by London Transport. These numbers were not theoretical. The Routemaster passed its tilt test with a margin to spare, confirming on paper and in practice that stability was now engineering, not assumed. The Routemaster's blueprint became the template for every double-decker that followed, making it the definitive turning point in the fight against rollover. Elliot Chen stands beside a stripped-down chassis, pointing to the dense cluster of hardware packed beneath the passenger floor. The engine, a solid mass of metal, sits just 0.7 meters above the road, deliberately low, anchoring the bus's heaviest component as close to the ground as possible. Next to it, the transmission and fuel tank share the same underfloor space. In earlier designs, these elements once rode higher, but now, every kilogram is counted and placed with intent. Lowering the fuel tank alone, from upper deck to undercarriage, drops the center of gravity by 9 centimeters, a small shift with outsized consequences for stability. Steel ballast plates, each weighing 150 kilograms, are bolted between the axles. They don't take up passenger space, but their effect is critical. Ballast at floor level acts as a counterweight, increasing the stability margin without raising the bus's profile. The track width measures 2.5 meters, forming a broad base that resists tipping even when the upper deck is full. Suspension is handled by air springs rated at 150 kilonewtons per meter, tuned to absorb bumps but stiff enough to limit body roll. Every component below the seat line isn't just functional. It's a calculated step in keeping the center of mass low, translating regulatory requirements into physical reality. Elliot Chen launches a simulation dashboard, pulling up the digital model of a modern double-decker bus. The software cycles through thousands of cornering scenarios, each one tracking the precise moment when the center of gravity approaches the edge of the stability triangle. The regulatory anchor for these calculations is CER66. Certification requires every new design to withstand a static tilt of 28 degrees without tipping. In practice, manufacturers target a safety margin well above this baseline. The simulation outputs a stability margin, or SM, defined as the ratio of the measured tilt angle to the regulatory minimum. For current models, SM values reach or exceed 1.4, meaning the bus can handle 40% more tilt than the legal threshold before any wheel leaves the ground. Volvo's engineers take this further. Their virtual testing environment runs Monte Carlo simulations, varying passenger loads, tire pressures, and road conditions. Across more than 10,000 runs, the calculated risk of tip-over remains below 0.1% at lateral accelerations up to 0.53 g, the equivalent of a sharp, high-speed turn. This level of confidence is not theoretical. Active roll control systems, linked to air suspension, adjust stiffness in real time, counteracting body lean and maintaining a nearly level chassis even under uneven loading. The result is a quantified safety margin, validated both in simulation and on the test rig, that keeps the double-decker upright in conditions far beyond everyday operation. Elliot Chen gestures toward a cutaway rendering of a new electric double-decker. Under the passenger floor, a dense bank of lithium-ion batteries stretches nearly the full length of the chassis. Each module, weighing several hundred kilograms, sits lower than any engine or fuel tank from the diesel era. The effect is measurable. The center of gravity drops by 15 centimeters compared to conventional models. This shift would have taken decades of incremental redesign in the past. Structural engineers now use the battery pack as a stressed member of the chassis, increasing rigidity by 22% in finite element simulations. This stiffer, heavier floor resists twisting forces that once plagued older designs, further anchoring the upper deck. When subjected to the regulatory tilt test, the electric prototype holds steady at 32 degrees before a single wheel lifts, 4 degrees higher than the legal minimum. The same principle that once called for steel ballast now finds its modern form in battery mass. BYD and Wrightbus both exploit this logic, using underfloor battery packs to guarantee that even as propulsion evolves, the foundation of double-decker stability remains unchanged. Today's double-decker bus is a machine defined by data, not myth. Its stability is calculated to the degree, its center of gravity measured in millimeters. As cities adopt new electric fleets, these engineering fundamentals remain non-negotiable. Stability isn't an accident, it's a standard. The science keeps every journey upright. Share your thoughts below.